In this lesson, we're going to take our first look at organic reactions, starting off with redox chemistry and specifically reductions. A big part of studying organic chemistry is learning reactions. There are only 6 fundamental types of organic reactions. First, we have rearrangements. A rearrangement is just a reaction in which atoms move within the molecule, creating new bonds and breaking old bonds. Essentially, it's the transformation of one constitutional isomer into a new constitutional isomer. So here you can see that these two molecules in this reaction have the same formula, but they are different structurally. The atoms are connected differently. That's a rearrangement. Next, we have substitutions. A substitution is simply when one atom or group of atoms is replaced by another. So here you can see that in the organic molecule, this bromine atom is going to be replaced by a fluorine atom. Then we have additions. An addition is when one molecule is literally added across the pi bond of an organic molecule. So if you look at this reaction, here we have an alkene reacting with HBr, and the entire HBr molecule was added across that pi bond. Eliminations are essentially the reverse of addition. An elimination is when a molecule is eliminated to form a new pi bond. So here we have this alkyl halide, and it forms a new pi bond. It forms an alkene, and as a result, another molecule, HBr, is formed. So it eliminated that HBr molecule to create a pi bond. The last two reaction types are reactions you've no doubt heard of before: oxidation and reduction. Now, you may have learned one or two mnemonics in some other chemistry courses that can help you to remember what oxidation and reduction are. First, there's Leo the lion goes grr, and that stands for loss of electrons is oxidation and gain of electrons is reduction. To me, that one's kind of wordy. I prefer oil rig, which stands for oxidation is loss of electrons and reduction is gain of electrons. When dealing with redox reactions on things like metals, the metal was literally gaining or losing an electron. Copper, for example. Copper can exist in 3 oxidation states: copper 0, copper 1, and copper 2. When copper is oxidized from copper 0 to copper 1, it literally lost an electron. When copper is reduced from copper 1 to copper 0, it literally gained an electron. Now, the covalently bonded atoms in an organic molecule don't lose and gain electrons, not in the literal sense. When a carbon or other covalently bonded atom is oxidized or reduced, it's not losing or gaining an electron, but it is gaining or losing electron density. So those mnemonics still work. You just have to add the word density after electron. So oxidation is a loss of electron density, and reduction is a gain in electron density. Now, the way that a covalently bonded atom gains or loses electron density is through manipulations of the number of bonds it has to electronegative atoms. An electronegative atom is going to pull electron density away from the atom it's bonded to. So an oxidation is an increase in the number of bonds to electronegative atoms. Oftentimes, oxidation results in a decrease in the number of bonds to hydrogen, and if either of these two things is happening, it's considered an oxidation. So if you look at this example, you can see that that middle carbon has one bond to oxygen, and it's going to a ketone, which has 2 bonds to oxygen. So that represents an increase in the number of bonds to an electronegative atom, so it's an oxidation. Note that that carbon also had 1 hydrogen on it in the reactant and 0 hydrogens in the product, so it's also an oxidation from that perspective. Conversely, a reduction would be a decrease in the number of bonds to an electronegative atom, or again, an increase in the number of bonds to hydrogen. Can be either or, often both. So if you look at this example, we have a ketone, and that central carbon has 2 bonds to the electronegative oxygen, and in the product, the alcohol has only 1. So it decreased the number of bonds to electronegative atoms. It's a reduction. The carbonyl carbon also has 0 bonds to hydrogen, and the product, that carbon has 1 bond to hydrogen. So it increased the number of bonds to hydrogen, and it's a reduction in that way as well. Covalently bonded atoms, like carbon, can have a variety of different redox levels. A redox level is nothing more than the number of bonds that atom has to electronegative atoms. A redox level is not really the same as a true oxidation state, although the terms are often kind of interchanged. Redox levels themselves are simpler than true oxidation states and generally more useful when learning fundamental redox reactions. So if we look at the possible redox levels for carbon, carbon can have up to 4 bonds, right? It has 4 valence orbitals, it can make 4 covalent bonds. And that means that there are actually 5 possible redox levels, because carbon can have as many as 4 bonds to electronegative atoms, but can have as few as 0. So here in this table, I have examples of organic compounds where we can see carbon in the 5 different redox levels. So carbon in the 0 redox level is typically a carbon that's bonded to other carbons and hydrogens. In other words, it has no bonds to electronegative atoms. Things like alkane carbons. Carbon in the first oxidation state is going to have 1 bond to an electronegative element. So things like simple alkyl halides, where you have a carbon to halogen bond, and alcohols, where you have a carbon oxygen bond. Those would be carbon in the first redox level. Carbon in the second redox level is going to be when carbon has 2 bonds to electronegative atoms. And these are almost always aldehydes and ketones, where you actually have 2 bonds to the same electronegative oxygen. We see carbon in the third redox level in certain other carbonyl compounds like carboxylic acids and amides and nitriles. In each case, you can see that carbon is bonded 3 times to an electronegative atom. And then lastly, carbon in the fourth redox level are things like carbon dioxide, where we have a central carbon that is double bonded to 2 separate oxygens, giving it 4 bonds to electronegative oxygen, or other carbonyl compounds like this compound here, which is called urea. And you can see that it has 4 bonds, 2 to electronegative oxygen and 2 to electronegative nitrogen. So when it comes to looking at oxidations and reductions on covalently bonded atoms like carbon, rather than calculating true oxidation states, we simply look for changes in the redox level. An increase in redox level during a reaction is going to be an oxidation, and a decrease in the redox level during a reaction is going to be a reduction. So the first reactions we're going to look at are reductions. And we're going to break down reductions into 3 subcategories. The first subcategory are hydrogenations. Hydrogenation is literally adding hydrogen, H2, across a pi bond. Hydrogenations are really useful for reducing pi bonds that are not highly polar. So in my first examples here, we're looking at carbon-carbon pi bonds, and that means alkenes and alkynes. In the first reaction, we have an alkene reacting with hydrogen gas and a catalyst, palladium, specifically palladium absorbed onto carbon. Now, if you've never seen an organic reaction before, this may look kind of strange to you. Normally, we think of reactions as a bunch of reactants on one side of an arrow and a bunch of products on the other side of an arrow. Organic chemists often do this a little bit differently. Organic chemists tend to visualize reactions as manipulations of carbon skeletons. So the way we draw reactions is to put the main organic compounds on the left as a reactant, the product on the right, and then the reagents that were necessary to make that transformation occur are drawn above and below the arrow. And there's no meaning as far as above and below, it all means the same stuff. Typically we start writing above the arrow and then below as necessary. So in this case, we're taking this alkene, reacting it with hydrogen gas in the presence of a palladium catalyst, and you can see that it transforms that alkene into an alkane. We literally added hydrogen gas across that pi bond. In the left structure, the leftmost carbon has 2 hydrogens on it, and the middle carbon has 1. And you can see that in the product, the leftmost carbon has 3 hydrogens on it, and the middle carbon now has 2. So it's a reduction in the sense that those 2 carbons experienced an increase in the number of bonds to hydrogen. Hydrogenation also works on alkynes. Now in an alkyne, you have 2 carbon-carbon pi bonds. And if you use the classic hydrogenation conditions of hydrogen gas and palladium on carbon as a catalyst, it will actually add hydrogen across both those pi bonds. In other words, it's going to add 2 molecules of hydrogen gas. You see here that the product is again an alkane. And the 2 alkyne carbons, they both experienced an increase in the number of bonds to hydrogen. In the reactant, both the alkyne carbons actually have 0 bonds to hydrogen, and in the product, each has 2. So an increase in the number of bonds to hydrogen is a reduction. Now it is possible to add only 1 molecule of hydrogen gas to an alkyne. If you think about it, that would remove 1 of the pi bonds, adding hydrogen across it, and leave 1 of the pi bonds behind, and that would give an alkene. In order to do that, we need to use a different catalyst, something called Lindlar's catalyst. Lindlar's catalyst is actually another palladium catalyst, but it's sort of contaminated to make it less reactive. Lindlar's catalyst is just strong enough to make the alkyne react, but prevent the alkene from reacting. Note that the 2 hydrogens actually ended up on sort of the same side of the alkene, right? and that's true for hydrogenation reactions. Now, there are some other functional groups that have relatively non-polar pi bonds. Some carbon-nitrogen pi bonds and some nitrogen-oxygen pi bonds can also be reduced through hydrogenation. So here we have a nitrile. It actually has two carbon-nitrogen pi bonds. Hydrogenation, again with palladium on carbon, will add two hydrogen molecules across those two pi bonds, resulting in the formation of an amine. And if you look, the carbon of the nitrile went from having 0 bonds to hydrogen to now having 2 bonds to hydrogen in the product. So it's a reduction from that perspective. But that carbon also went from having 3 bonds to an electronegative nitrogen and now only has 1 bond to an electronegative nitrogen in the product. So it's a reduction from that perspective as well. Another functional group that has a carbon-nitrogen pi bond is an imine. An imine is just a carbon-nitrogen double bond. Here, because there's only one pi bond, we can only add one molecule of hydrogen, in this case again forming an amine. And then lastly, an example of a nitrogen-oxygen pi bond being reduced. So here we have a nitro group. These are really common on this ring system called a benzene ring. Now, one of the oxygens in that nitro group is double bonded to the nitrogen. So that means we have a nitrogen-oxygen pi bond. So hydrogenation of a nitro group is going to result in the formation of an amine. So here we've transformed that NO2 into an NH2 group. The next category of reductions are the metal hydride reductions. A metal hydride is a reagent that has a metal bonded to hydrogen atoms. Metal hydride reductions are really useful for reducing more relatively polarized pi bonds, typically carbonyls that have a CO pi bond, and also carbon-nitrogen pi bonds, so things like nitriles. So here I've got examples of some of the more important metal hydride reactions. First up, we have the use of sodium borohydride. Sodium borohydride only will reduce aldehydes and ketones specifically, and it will reduce them down to an alcohol. So here we're starting off with this ketone. You can see that that carbonyl carbon is in the second redox level, and it reduces that carbonyl down to the first redox level. A similar but more powerful reagent is lithium aluminum hydride. Lithium aluminum hydride will also react exactly the same way with aldehydes and ketones, transforming them into alcohols. You'll note that in this reaction, we have these numbers in front of each of the reagents. Those numbers represent an order. In other words, the lithium aluminum hydride must be added first, and then when it is done doing what it's going to do, then you add the acid, the hydronium. Those numbers are important. Without those, the reaction will not work correctly. Now, I mentioned that lithium aluminum hydride is a more powerful metal hydride than sodium borohydride, and that means that it can react with some other types of carbonyl compounds. So here I have an example of an ester reacting with lithium aluminum hydride, again to form an alcohol. So in this case, the carbonyl carbon went from the third redox level, again down to the first redox level. Lastly is an example of an amide reacting with lithium aluminum hydride. And what's different about this reaction is that the product is not an alcohol. It's actually an amine. And you have to remember that whenever you do a reduction of a nitrogen-containing functional group, it's typically the nitrogen atom that kind of sticks around. So in this case, that carbonyl of the amide starts off in the third redox level and is reduced down again to that first redox level. But in this case, we actually end up with a carbon-nitrogen bond in the product. The last category of reductions we're going to look at are deoxygenation reactions. Deoxygenation is the removal of an oxygen atom from an aldehyde or a ketone, essentially making an alkane or an alkyl group. So we've got two reactions that can accomplish this. First is the Wolf-Kishner reduction. So here I have an example of a ketone, and we're reacting this with this funky molecule here. This is hydrazine. Reaction of an aldehyde or a ketone with hydrazine under basic conditions will result in the formation of an alkane in this case. Another way to do the exact same process is called the Clemmensen reduction. So here I have the same ketone, but now different conditions. Here we have another funky reagent. This is zinc mixed with mercury. It's called a zinc-mercury amalgam, and an amalgam is just a special kind of alloy. Regardless, when you treat an aldehyde or a ketone with this zinc-mercury amalgam under acidic conditions, it's going to do the exact same thing. It's going to remove that oxygen, replacing it with two hydrogen atoms. Just remember that these reactions don't work on all carbonyls. They only work on aldehydes and ketones specifically.